before we embark on solving the sheet, just a few more remarks. Not closing remarks, but some add-on to whatever we have learned in matrices by this time. Mostly jargon. So, we have some more classification for matrices, some more entities towards classification of matrices. We have what are called triangular matrices. This is defined for square matrices, order n by n. We define triangular matrices only for square matrices. See, if I have a square matrix, it has a diagonal element. It has a diagonal element, right? This is a square matrix A. It has a diagonal element which divides elements equally on two sides of the diagonal, right? It has a diagonal. Now, so Aij represents the elements of this matrix. Aij, I is the row index, J is the column index. For all elements that lie on the diagonal, I will be equal to J, isn't it? For all elements that lie along the diagonal, for all elements that lie along the diagonal, I will be equal to J, right? Below the diagonal, we have I less than J or greater than J? I greater than J, I greater than J. Yes or no? I will be greater than J for elements that lie below the diagonal. How many of you don't understand this fact? All of you understand that all elements Aij lying below the diagonal would have the row index more than the column index. Row index more than the column index. For all elements above the diagonal, I will be less than J. Yes or no? See, we have A11, A12, A13, A14. So I is less than J. Do you see that? Right? Now, two kinds of matrices that are encountered in as far as triangular matrices are concerned. We have what's called an upper triangular matrix . We have what's called an upper triangular matrix. In the upper triangular matrix, all elements below the diagonal will be 0. All elements below the diagonal will be 0. Only the non-zero elements will lie only on the elements above the diagonal. That means in the upper triangular matrix, Aij will be 0 for I greater than J. That means below the diagonal for I greater than J. That means all elements below the diagonal will be 0. Above the diagonal may or may not be 0, but below the diagonal, that means for I greater than J's elements below the diagonal, they will be 0. That's an upper triangular matrix. And then we have what's called a lower triangular matrix. Now in the lower triangular matrix, all elements above the diagonal will be 0. All elements above the diagonal will be 0. That means for I less than J, that is elements above the diagonal, we'll have Aij equal to 0. That's the lower triangular matrix. Right? Yes or no? And then we've already learned what's a diagonal matrix. A diagonal matrix is, say, D1, D2, D3, for example, a 3 by 3 matrix. And all elements Other than this, the diagonal elements will necessarily be 0. Now, this is both an upper triangular as well as lower triangular. A diagonal matrix is both upper triangular as well as lower triangular. Yes or no? You know what I'm saying? Now, some more terminology related to matrices. We have what's called a nilpotent matrix. Nilpotent matrix. Nilpotent matrix. See, if for a matrix A, I can find a positive integer p. I can find a positive integer p. If for a matrix A, I can find a positive integer p. P is a natural number, say greater than 1. Positive, right? Natural number greater than 1. If for a matrix A, I can find a natural number p greater than 1, for which A to power p is a null matrix, is not 0, is a null matrix. Right? Then A is called a nilpotent matrix. A is called a nilpotent matrix. And the smallest p for which this can happen, the smallest positive integer p for which this can happen is called the index of the nilpotent matrix. Is called the index. P is called the index of the nilpotent matrix. For example, if I have a matrix A such that A square is a null matrix, A square is a null matrix, then A is nilpotent of index 2. A is nilpotent of index 2. Right? Now we have again what's called an involutory matrix. All square matrices, these are all square matrices, order n, all square matrices of order n, say. A is called an involutory matrix if A square is I, identity matrix. If A square is I, then A is called an involutory matrix. If A square is I, then A is called an involutory matrix. Then we have what's called idempotent. Idempotent matrix A. If A square is A, then A is called an idempotent matrix. If A square is A, then A is called an idempotent matrix. A is called an idempotent matrix. Right? If A square is A. Now, some more things. Can I wipe this off? Now, if I have a matrix A, then A bar is the matrix of its conjugates. That means, say if I have a matrix A which is 2, 3 plus I, 5 minus I, right? Then A bar simply is a matrix in which I take the conjugates of all elements of A. Complex conjugates of all elements of A, that's A bar. Which is, now complex conjugate of 2 will be 2. Complex conjugate of 3 plus I is going to be 3 minus I. Of 5, 5. Of minus I, plus I. Right? So A bar would be like 2, 3 minus I, 5 I. That's A bar. It's just the conjugate of that matrix. That's the conjugate of that matrix. That means if A bar is the matrix B, then all that it means is Bij is, say the elements here are Aij, Bij would be Aij bar. That's all. That's all, right? And some simple properties that you can see around conjugate of matrices. If alpha is any number, real or complex, if alpha is any number, real or complex, then alpha into A. See, A is a vector. So we eventually, these matrices are vectors. In a very generalized sense, these are actually vectors doing certain things. I'll come to that when the time is right, but as of now, let me tell you that that's the most generalized notion of vectors. Okay, alpha is a scalar, which is any number, real or complex. All right, and I take the conjugate of this, then that's like alpha bar A bar. That's like alpha bar A bar. Right? Bar of alpha A would be where alpha is a number, real or complex. It's a scalar. We call it a scalar. Then we have, say, A plus B bar conjugate. That's like A bar plus B bar. You should be able to establish all of this independently. Very easy to see properties. Bar of A plus B would be bar of A plus bar of B. A and B are not numbers. A and B are matrices. Similarly, AB bar would be A bar B bar. Product, conjugate of a product would be product of the conjugates. Right? Now, if I have a matrix A, then we define this operation A theta. We define this operation A theta as being composed of two operations. When I say find A theta, it means first take the conjugate of A and then transpose A. It means take the conjugate of A and transpose A. That's A theta. A theta means take the conjugate of A and transpose A. Say for example, if A is 1 plus I, 2 minus I, 3, 2 plus 3I, 5I, minus 3I, 6, 2I plus 1, and 5I plus 2, suppose. That's A. Then what would A bar be? A bar would be simply 1 minus I, 2 plus I, 3, 2 minus 3I, minus 5I, 3I, 6, 1 minus 2I, and 2 minus 5I. That's A bar. That's A bar. And now if I take the transpose of this, A bar, and then I transpose this, that means I convert rows into columns and columns into rows, then that's going to be the matrix 1 minus I, 2 minus 3I, 6, 2 plus I, minus 5I, 1 minus 2I, and then 3, 3I, and 2 minus 5I. That's taking the conjugate and transposing. This operation is called A theta. That's called A theta. Taking the conjugate and transposing. Hey, now do you realize nothing would change if I interchange the operation? That means if I transposed A and then took the conjugate, I'll get the same matrix. Right? That means essentially T is the same as A transpose and then the bar of this. A transpose and the bar of this. Yes or no? I could have swapped the operations. Taken transpose and bar, or bar and then transpose. Yes or no? Right? Clear? Now, based on this definition of A theta, A plus B theta is going to be A theta plus B theta. A and B are matrices, right? Lambda is a scalar. Lambda A theta. Now, again, you know, this lambda could also have been a complex number. Could also, this is a scalar and A is a matrix. When I say lambda A theta, what according to you should be the output of this operation? Lambda bar. I'll have to take lambda bar, right? Instead of lambda, it will become lambda bar and then A theta. Of course, if lambda is real, lambda bar will be equal to lambda. If lambda is purely imaginary, lambda bar will be minus lambda. Right? And then I have an operation AB theta. Think about this. Huh? That's going to be the reversal rule. That's going to be the reversal rule. You want to check. AB theta would be B theta, A theta. This reversal rule will apply. Now, I define certain matrices A as Hermitian matrices. Hermitian matrices. A is a Hermitian matrix if A is the same as A theta. That means when you take the conjugate and transpose, you get A. What are you doing here? Taking the conjugate and transposing, or transposing and then taking the conjugate, and you get back to A. Then the matrix A is called a Hermitian matrix. The matrix A is called a Hermitian matrix. Right? Now, and then we have what's called skew Hermitian. A would be minus A theta. That's a skew Hermitian. That's a skew Hermitian. Now, one very simple, easy observation. See, suppose A is a Hermitian matrix. Suppose A is a Hermitian matrix. Then A theta, suppose, is the matrix B. A theta is the matrix B. Then the ijth element of this matrix, is going to be AJI transpose. Do you realize that? Conjugate. The ijth element of this matrix is the jith element of A with a conjugate. Yes or no? Do you all understand this? Now, that means, look at A in a Hermitian matrix is A theta. Ijth element of this is Aij. And ijth element of A theta, this is A theta. Ijth element of A theta would be AJI conjugate? Yes or no? A theta is B. What is the ijth element of B? AJI, B bar. A theta is B. So Bij is AJI conjugate. Right? Yes or no? Now, as a special case, in a Hermitian, this is a Hermitian matrix. If I is J, what does it represent? The diagonal elements. I equal to J represents the diagonal elements. So put I equal to J in a Hermitian matrix. That means I'm talking of AII equal to A bar II. That's the property true for the diagonal elements in a Hermitian matrix. Put J equal to I. AII in a Hermitian matrix, AII is A bar AII. That means the diagonal elements are equal to their conjugates. That means the diagonal elements must be real numbers. These are diagonal elements. The diagonal elements are equal to the conjugate of themselves, right? That means the diagonal elements must be real. That means in a Hermitian matrix, the diagonal elements are real. Certainly, right? In every Hermitian matrix, diagonal elements have to be real. Clear? Yes or no? Clear? Can I wipe this off? Now, in a skew Hermitian matrix, A is minus A theta. Aij then is minus AJI conjugate. Yes or no? That's what it means. Because A theta has elements Ij, which is AJI bar. The ijth element of A theta is AJI bar. Yes or no? That means this A theta can be written as minus AJI bar. Now, for diagonal elements, I equal to J. This is for a skew Hermitian now. So, for diagonal elements, I equal to J. That means AII is minus A bar II. AII is minus A bar II. That means the diagonal elements are negative of their conjugates? The diagonal elements are negative of their conjugates? That means the diagonal elements must be purely imaginary. That means the diagonal elements must be purely imaginary. Anushka. Okay, 0 into I say, then, right? Right? So, diagonal elements are purely imaginary. Diagonal elements are purely imaginary. Yes or no? Do you remember I had mentioned to you that every matrix, by and large we are talking of square matrices, every matrix could be looked upon as a sum of a symmetric and a skew symmetric matrix. I had also offered a proof for that. Now I go on to say that every matrix A can be looked upon also as sum of a Hermitian and a skew Hermitian matrix. You should establish this yourself. Every matrix A could be looked upon also as a sum of a Hermitian and skew Hermitian matrix. Right? Think about it. Every matrix could be looked upon as a sum of a Hermitian and skew Hermitian matrix. Raise both sides to power theta. I mean, not raising to the power theta, perform that operation theta, and just like I proved for symmetric, skew symmetric, you will get the result, and then add, etc. Now, again, in a square matrix, A22, these are the diagonal elements. These are the diagonal elements, and then of course there are other elements. Right? And then there are other elements. This is a matrix A. We define what's called the trace of a matrix. Trace of A. TR A. Trace of the matrix A is the sum of the diagonal elements. Is the sum of the diagonal elements. That means it's going to be summation AII I equal to 1 to n. That's the trace of the matrix. Just this A11 plus A22 plus ANN, that's the trace of the matrix. And you know, I will have a few remarks after this, but let me just introduce this terminology in a very dumb way. Trace of lambda A, where lambda is a scalar, A is a matrix, would be lambda times trace of A, would be lambda times trace of A. Trace of A plus minus B is going to be trace of A plus minus trace of B. Trace of A plus minus trace of B. The important thing is trace of AB think about this. Trace of AB for your consumption. What would trace of AB be? Trace of AB. Okay. No. No, no. We'll give you a while to think about this, but by the time the class gets over, you should be able to tell me what trace of AB is. Now, we define, if I have a square matrix A, if I have a square matrix A, and I multiply it with another matrix X, and I multiply it with another matrix X. If I have a square matrix A, and I multiply it with another matrix X, X need not be a square matrix. X need not be a square matrix. But I end up getting a scalar times X, and I get a scalar times X. If I have a matrix A, on multiplying A with X, I get a scalar lambda times X. Then this gives me like a AX minus lambda X is 0. AX minus lambda X is 0. This is like A minus lambda times a unit matrix into X, that's 0. That means the determinant of this will be 0. I'm assuming determinant of X is not 0. I'm assuming determinant of X is not 0. In fact, determinant of X may not even exist because X may not be a square matrix. X may not be a square matrix. If this is 0, that means it's a null matrix. That means it's a null matrix. Now, obviously, the determinant of this matrix must be 0. Now the value is 0. That was a 0 matrix, a null matrix. Now it's a value. Determinant means now it's a value. It's a value, right? Now, which clearly means that determinant of A minus lambda I would be 0 for A minus lambda I would be 0 for some values of lambda, for some values of lambda. For some values of lambda, determinant of A minus lambda I must be 0. And this equation is called the characteristic equation for the matrix A. It's called the characteristic equation for the matrix A. It's called the characteristic equation for A. Now the question is, given A of a certain order, a square matrix of a certain order, how many values of lambda I obviously will have to be of the same order to make A and lambda I commensurate, right? If A is of order n, the unit matrix I will also be of order n, right? Suppose I have a matrix A. which is say A, B, C, D, right? Suppose it's a 2 by 2 matrix. Suppose it's a 2 by 2 matrix. And I want to find lambda. Lambda is called a characteristic root of A. Lambda is called a characteristic root of A. This equation is the characteristic equation for A. Lambda is the characteristic root of A. Now A is a 2 by 2 matrix. A minus lambda I is like A minus lambda, B minus lambda, C minus lambda, D minus lambda. Yes or no? That's A minus lambda I. Do you realize how? Right? Do you all understand how this was performed? This is A minus lambda I? Nahin, nahin na? Not very sure? Nahin na? A is A, B, C, D minus lambda I, which is 1, 1, 0, 0. So this will be 0. So obviously, when I multiply, I'll have lambda here, lambda here. So for sure, this will not be there. A minus lambda, B, C, D minus lambda. That's A minus lambda I. That's A minus lambda I, isn't it? This is lambda I. A minus lambda I will be A minus lambda, B minus 0, C minus 0, D minus lambda. That's A minus lambda I. That's A minus lambda I, right? This is A minus lambda I. Now, the determinant, what would be the determinant of this? The determinant of A minus lambda I is going to be A minus lambda into D minus lambda minus BC. That's determinant of A minus lambda I, isn't it? A minus lambda into D minus lambda minus BC. That's determinant of A minus lambda I. Now, this will be 0. You get a quadratic in lambda. Do you realize you get a quadratic in lambda? You get like a L lambda squared plus M lambda plus N equal to 0 kind of a thing, which will give me 2 values of lambda. Which will give me 2 values of lambda. Yes or no? You will get a polynomial of degree 2 in lambda. If A is a 2 by 2 matrix, if A is a 2 by 2 matrix, then the characteristic equation will give me a polynomial of degree 2 in lambda. The characteristic equation will give me a polynomial of degree 2 in lambda equal to 0. Right? This is the characteristic equation for A. This is the characteristic equation for A. Now, there is a world of things around this, and you know, unfortunately, I'm not digging deep into this. For the time being, I'm only introducing terminology and nothing else. But there is lot of fascinating stuff around this. But what is it that you get out of the characteristic equation equal to 0? You get a polynomial of degree 2 in lambda. You get a polynomial of degree 2 in lambda. If A was of degree 3, then the characteristic equation will reduce to a polynomial of degree 3 in lambda. See, you will have along the diagonal lambda, 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 you will get lambda cube kind of a thing. If you have a matrix of degree of order n, if A is a matrix of order n, you will get a polynomial of degree n in lambda. You know what I'm saying? So in general, this determinant of A minus lambda I equal to 0 in general will give me something like A naught lambda to power n plus A1 lambda to power n minus 1 plus A2 lambda to power n minus 2 plus An equal to 0, where lambda is the characteristic root of A. Lambda is the characteristic root of A. It's a polynomial of degree n in lambda. It's a polynomial of degree n in lambda. This is f lambda. This expression is, say, f lambda. This expression is f lambda. This expression is f lambda. Clear? Now, what I want to tell you is this equation is way beyond what I have just mentioned as very mundane stuff. What will happen is, this is my characteristic equation. This is my characteristic equation in the characteristic root lambda. But the matrix A, see, lambda is a scalar. The matrix A will also satisfy this equation. That means f of A, that will be a matrix equation. Now that will be a matrix equation. Let me tell you that f of A will also be 0. Let me suggest that f of A will also be 0. A naught, A to power n. Now that's matrix A into A into A n times. Minus A1, matrix A into A n minus 1 times. If you perform that operation instead of lambda, you perform this operation on the matrix A. That will also produce a null. That will produce a null matrix. Not 0, a null matrix. It will produce a null matrix. Only difference is this an will become ani, because now you are doing all matrix operations, right? So this will become ani. So you know what I'm saying? Huh? Right now? So essentially then what would happen is, the following will happen. A naught, A to power n plus A1, A to power n minus 1. I have not proved it, and it's not that trivial. Plus an, I is a unit matrix of the same order. That must be 0. This equation actually is called what is called a Cayley-Hamiltonian equation. Cayley-Hamilton's equation. It's a Cayley-Hamilton's equation, and it has far-reaching consequences. What you can do is, sometimes they'll give you a matrix A. Let me see if there is something in the sheet that will drive home this point a little better. Let's look at problem number 13. Maybe it works. Let me see. I'm not very sure. Let's try number 13 to see if this Cayley-Hamilton applies here. Can I wipe this off? See, A is this matrix which is like 1, 2, 0, 2, minus 1, 0, 0, 0, minus 1. Right? Let's see what A minus lambda I is. The matrix A minus lambda I. See, what is I here? I, as you can see, is 1, 1, 1, 0, 0, 0, 0, 0, 0. That's I, right? What is lambda I? Every element will get multiplied with lambda. So lambda I would be lambda, lambda, lambda. Right? So A minus lambda I, the matrix A minus lambda I is going to be 1 minus lambda, 2, 0, 2, minus 1 minus lambda, 0, 0, 0, minus 1 minus lambda. Yes or no? That's A, the matrix A minus lambda I. Do you all understand this? Do you all understand this? Right? Now, the determinant of this A is a matrix of order 3. Right? 3 by 3 matrix. So I should get a cubic in lambda when I take the characteristic equation. See, this is what you'll get. So determinant of A minus lambda I is what? 1 minus lambda into minus of 1 plus lambda into minus of 1 plus lambda. So 1 plus lambda minus 2 into 0 minus, so plus 1 plus lambda equal to 0. Do you realize it's a cubic in lambda? Do you see that it will be a cubic in lambda? Yes or no? Now what we are asked to establish here is, so this will be some expression f of lambda. This will be some expression f of lambda, right? I'm assuming I have not made a mistake. If I have, fix it. Okay. Now realize that what we need to establish here is 5a inverse is a square plus a minus 5i. This is what I want to establish here. Given a. I'm just seeing if this works. I'm not even sure if it will work, but we are just trying it out. Okay. So this is equivalent to, if I multiply both sides by a, then a inverse a would be I. I'm multiplying by a. Post multiplying. This is post multiplying. This is a cubed. This will be a squared. I into a would be a. I into a would be a. And this is 5i. This is 5i. That means a cubed plus a squared minus 5a minus 5i is 0. Right? That means I'm expecting f lambda, see if f lambda turns out to be lambda cubed plus lambda squared minus 5 lambda minus 5. Is f lambda turning out to be this? Check this. This is f lambda. You know what I'm saying? If f lambda turns out to be this, then f of a, this is f lambda, this is f lambda. If I have not goofed up the computations. If I have, you fix it. Okay? If all is good on f lambda is determinant of this. Right? Then f of a will be 0. F of a will be 0. That means, see, f of a is this. That means I should have got like a lambda cube plus lambda squared minus 5 lambda minus 5 equal to 0 should have been my equation cubic in lambda. See if that makes sense or not. It's not. Minus lambda cube, then minus lambda squared? No? That's what I'm saying. You fix that. If that's the case, you fix it. Minus lambda squared are na? Then this will be plus 5 lambda plus 5. Transpose. I mean, don't bother me about your computations. Fix that computation and see if you are getting. Huh? You're not getting this? Lambda cube plus lambda squared minus 5 lambda? Check that out. Okay, like I said, it might work sometimes. It might work sometimes. Right? So there are times, you know, they'll give you a matrix equation to be established. You write down the characteristic equation involving lambda and then replace lambda by a. F of a becomes 0. I was expecting, it was just my guess, I was expecting that if I have to prove this, essentially, you know, a cube plus a squared minus 5a minus 5i equal to 0, then I was hoping that my characteristic equation will turn out to be lambda cube plus lambda squared minus 5 lambda minus 5. I was hoping that will happen. Huh? It's happening? So then where is the confusion? Are you getting f lambda equal to this? Then what's the glitch? This was plus 4? Okay. So yeah, I said I could have